So this is where I'd like to actually start part two of the atmospheric chemistry saga, I guess. Right? So we're now going into carbon maintenance, dioxide maintenance, nitrogen oxide maintenance in the atmosphere, formation of acid rain, pollutants from exhausts, from hydrogen fuels, etc. These are things we're going to be looking at now, right? So the importance of maintaining carbon dioxide concentration in the atmosphere. Now, the carbon cycle. The carbon cycle really describes the continuous movement of carbon through different parts of the Earth's system, right? Including the atmosphere, biosphere, hydrosphere, and geosphere, right? So the carbon exists in various forms, right? So it exists in carbonates, which are inorganic, and it also exists in organic matter, right? It and it transfers between carbon reservoirs, where carbon is stored, and carbon sinks, in which carbon is absorbed and removed from the atmosphere. Right? So, key carbon reservoirs. The atmosphere is a carbon reservoir. So, containing carbon primarily in the form of carbon dioxide and methane. It is most rapidly fluctuating reservoir. It is the most rapidly fluctuating reservoir because it constantly exchanges carbon with plants, oceans, and human activities. Right? So looking at stuff like that. The oceans also act as carbon reservoirs. They store carbon as dissolved carbon dioxide, bicarbonates, and other carbonates as well. The ocean acts as both a reservoir and a sink, absorbing large amounts of atmospheric carbon dioxide through gas exchange and biological processes. Please note, right, the oceans are one of the most important, sorry, not one of the most, it is the most important biome on this entire planet. If the ocean goes, we all go. The ocean is the most bioactive and biodiverse place that we have on the entire planet, right? So it's the most crucial carbon reservoir and carbon sink, right? Terrestrial biosphere is another reservoir for carbon. So it includes all land ecosystems, forests, grasslands, soil microbiomes, microbes rather, and animals. Right. So plants take in carbon dioxide for photosynthesis, and carbon is returned to the atmosphere through respiration and decay. We also have the lithosphere, or what we call the geosphere. So it stores carbon in forms of fossil fuels, so coals, oil, gas, right? Sedimentary rocks and carbonate minerals. So this is the largest reservoir but exchanges carbon with the atmosphere very slowly over geological time scales. So over millions of years. Alright? The last carbon reservoir example that I have here is fossil fuel reserves. So technically part of the lithosphere, but particularly relevant because human activities like combustion of fossil fuels, right, which is coal, oil, natural gas, etc., release stored carbon rapidly into the atmosphere. Alright? So the carbon reservoirs, the atmosphere, oceans, terrestrial biosphere including fossil fuel reserves, and the lithosphere. Alright? So the carbon cycle is here as well. We should know generally how that works. Right? However, this table summarizes release areas or points at which carbon dioxide is released into the atmosphere and also points at which it is uptaken into the atmosphere, right? So respiration, right? For respiration will release carbon dioxide, but for photosynthesis, carbon dioxide would be absorbed. We release carbon dioxide using when burning fossil fuels, right? When we have decomposition of organic matter as well, right? And we release carbon dioxide upon warming oceans, right? Do we understand how carbon dioxide is released from oceans when we have warming of the oceans? Would you guys understand that? Not quite sure. When I was tutoring biology unit 2, I explained this now. Go ahead. Alright, so warming of the oceans. As the temperature increases, right, the equilibrium of the reaction shifts to favor the products in this reaction that they have here, right? So the equilibrium will shift, alright? And we're gonna have the production of carbon dioxide. right? So more release of carbon dioxide. So we're looking at the production of the bicarbonate or carbonic acid there, right? So as the temperature increases, carbonic acid favors decomposition. So we increase the heat of the carbonic acid, and because it's a carbonate, and we spoke about thermal stability of carbonates in Unit 1 chemistry, right? It's something about that, right? So the carbonate will destabilize, decompose into carbon dioxide, water, and other dissolved carbonates, all right? So that is it there. Also, we release carbon dioxide to the atmosphere via volcanic activity. All right. So looking at stuff like that, disrupt the disrupted carbon cycle. We have to look at stuff like this. All right. So we know that the carbon cycle will remain that dynamic balance of carbon dioxide in the atmosphere, right? But there are different things that can disturb the balance of carbon dioxide in the atmosphere. So we can look at the natural balances and then look at what throws it out of balance. So natural balances. So plants absorb carbon dioxide from the atmosphere and converts it into organic molecules, right? So we're taking it from the atmosphere of respiration, right? These organisms, when they break down organic molecules rather, right, it releases carbon dioxide back into the atmosphere. We also have ocean atmospheric exchange, where carbon dioxide is continuously absorbed and released, right, from this ocean surface at equilibrium. The net flux is zero. So it's similar to vapor pressure, or we looked at separation, right? So it's similar to that. So the rate of evaporation and redissolution is basically the same, right? So if these processes are undisturbed rather, photosynthesis and respiration as well as oceanic absorption and release operate in a cyclical and self-regulating manner, right? So what we're saying, if these things continue to occur naturally, right, the balance of carbon dioxide, right, in reservoirs, right, and in the atmosphere will remain more or less constant, all right? But we have human-induced disruption. So looking at something like deforestation, large-scale removal of forests reduce the Earth's capacity for photosynthesis, right? That means that fewer trees means that less carbon dioxide is absorbed into the atmosphere, right? Additionally, when trees are burned or decomposed, stored carbon is released as carbon dioxide. So not only when we remove the trees, we have less photosynthesis, allowing carbon dioxide to remain in the atmosphere, but when we burn these trees, etc., right, it will add combustion of fossil fuels as well. When we burn fossil fuels, we release carbon dioxide as well as other chemicals into the atmosphere as well, right? So we'll now push the carbon cycle out of balance as we increase the amount of carbon dioxide in the atmosphere. Ocean temperature increase as well. It's linked with global warming. So warmer ocean temperatures reduce carbon dioxide solubility in water. That's another part of it, right? And the equilibrium involving bicarbonate and carbonate shifts, right, to produce carbon dioxide. The higher temperatures prefer dissociation of that bicarbonate, releasing more carbon dioxide into the atmosphere. This weakens the ocean's role as a carbon sink, further amplifying the greenhouse effect. So we're looking at things like that. All right. So how can we restore the balance between these things, between natural balances and human disruptions, right? We can participate in reforestation, right? Increasing the photosynthetic capacity of the earth, right? So forests also act as long-term carbon stores, carbon sinks, right? Sequestering oxygen, or well, not oxygen, but carbon into biomass and soil. We're also transitioning from to renewable energy rather, and reducing fossil fuels. This will now cut the carbon dioxide emissions, right? And we can also protect and restore marine ecosystems like mangroves, seagrass forests, right, and coral reefs, which can also enhance the natural carbon sequestration. Sequestering means basically taking from, right? So when we say we're sequester carbon from the atmosphere, we mean we're taking carbon from the atmosphere. All right. So we have some key terms to go through that are important for atmospheric chemistry here, right? So we have the greenhouse effect. So as we say, as Christine may say, it is common sense, right? We have been looking at these things from a taller time. Yes, the greenhouse effect and climate change is real, No, it is not real. All right. So I still to this day can't understand how persons think that climate change is a hoax and think that it's not real and thinks that it's just propaganda. I think that anybody who pushes that type of narrative that climate change and global warming is not real should mute their mics forever. It makes no sense. All right. But greenhouse effect, right? This is a natural and essential atmospheric process that helps to regulate the Earth's temperature, right? So greenhouse effect is not necessarily a bad thing, you know. It helps to regulate the Earth's temperature. But if we continue to increase greenhouse gases, right, the greenhouse effect will increase the temperature over the equilibrium point, right, and will now cause climate change. Without the greenhouse effect, the Earth would just be a snowball in the center of space, right? But with the effect now, it keeps a certain temperature for life to exist on the planet. But if we continue to increase, right, or intensify human activities, right, which leads to a greater amount of greenhouse gases, we now continue to increase the temperature over a tipping point that causes climate change. All right, so we have that there. So you have natural greenhouse effect. The natural greenhouse effect exists. It's fine, right? With solar radiation, right? Some is radiated out, some is trapped, right? Which is fine. It keeps a constant temperature on Earth. But with human enhanced greenhouse effect now, since we have more greenhouse gases, we trap even more of the heat and the UV radiation that is supposed to be released, right? So it constantly increase the Earth's temperature, moving from global warming to what some places are now calling global boiling, right? So if you guys can notice, each and every summer, every other summer, it is the hottest summer we have ever met. The hottest summer was in 2016, then 2017, then 2018, then 2019, going up, right? We can probably guess that this year we'll have the hottest summer on record as well, right? So the years will continue to getting hot. Yes, it keeps getting worse, right? And there will be a point of no return. Because that's how chemical reactions are. That's how ecosystems are. There we can. This is gonna continue to happen until there's a point in which whatever we do won't matter, right? Because we're just gonna have a rampant increase in the temperature. There are things that we can do to mitigate climate change. Yes, it would be non-reversible. Lovely. You're just quick fire, right? But yeah, so we're just looking at stuff like that, right? So global warming, right, refers to gradual increase in the average temperature on the Earth's surface over time, primarily due to the human-induced enhancement of the greenhouse effect, right? I'm looking at stuff like this: carbon dioxide, methane, nitrous oxide, water vapor. Water vapor is a significant variable, right? A lot of persons keep on forgetting water vapor, CFCs as well, and we can look at the relative effects, right, and the source of these things. Mhm. So we know that nitrous oxide is 300 times more potent than carbon dioxide. Methane is 25 times more potent, right? CFCs are thousands of times more potent than carbon dioxide. Water vapor can be variable, less potent and more potent, but because of the sheer amount of water vapor in the atmosphere, it is significant. What can we note about all these molecules, though? These molecules are all IR and UV active molecules that allows for the trapping of UV radiation in the atmosphere, right? So looking at stuff like that. Photochemical smog, now, as we stated it slightly before, but the photochemical smog is a type of air pollution characterized by a brown haze, primarily observed in urban environments during sunny days, right? Because if the day is sunny, we know that's more UV radiation, leading to more of the photolysis of nitrous oxide, right? So it is formed through a complex series of reactions involving nitrogen oxides, volatile organic compounds, and sunlight. Note, VOCs, which come from vehicle exhaust, gasoline, paint, and industry solvents, react with nitrogen monoxide and other radicals to produce Perioxy, perioxyacyl nitrates, right? So perioxyacyl nitrates, PANs, right? And other secondary pollutants. So these are secondary pollutants. Lovely. VOCs also slow down the recombination of carbon monoxide and ozone, which would otherwise limit ozone buildup, allowing ozone levels to accumulate near the ground in the troposphere. So looking at stuff like that. So looking at this now. All right, let me get my pointer. I will start on going through what's on here, right? So we have the nitrogen dioxide and the UV radiation leading to photolysis that will produce that extra atomic oxygen, which will now bind to create ozone. We spoke about that earlier. Ozone, so formed, oxidized, it can actually oxidize nitrogen monoxide to nitrogen dioxide and O2. So this reaction now would actually limit the production there, right? So the first reaction here is showing how we can create ozone at tropospheric levels. The second reaction is showing the depletion of ozone at tropospheric levels. But say we have atomic oxygen plus a hydrocarbon, right? We can create this type of free radical type of reaction, right? So we can end up with the creation of ketones and aldehydes, right? Which are extremely UV active compounds. And when these ketones and aldehydes react with nitrogen dioxide, they create the perioxalase acetyl nitrites or nitrates. The acetyl nitrates, right? So PANs, which are extremely dangerous at tropospheric levels. The presence of excessive ozone along with aldehydes, ketones, and PANs, right, contribute to photochemical smog. So all of them together create that brown smog. Let me go back to the picture that I had before. All of them together create that brown smog. This smog here, right? The photochemical smog here. The VOCs, the nitrogen dioxide, the sunlight, all of these things, the ozone, would create the photochemical smog. And you can imagine what the air quality in this area would be, right? How many diseases can be contracted from this area, not to mention how hot this area would be, right? It was extremely warm. This is why, for example, urban areas tend to be warmer than rural areas because there is photochemical smog. It may not be enough for you to see a brown haze, but there is photochemical smog around. Because I'm from Jamaica, in the Kingston area, Kingston is extremely hot compared to other rural areas. Kingston has industry and these different areas, right? These different things that will now contribute to photochemical smog, leading to a more hot or a hotter urban area as opposed to natural rural areas, right? So looking at stuff like that. The effects of products of combustion of hydrocarbon-based fuels now, right? We're looking at now specific pollutants. So carbon monoxide, which is the source is incomplete combustion in carbon-containing fuels, right? We know that carbon monoxide will bind to hemoglobin in red blood cells, forming carboxy hemoglobin, right? And this can cause carbon monoxide poisoning. We looked at this in Unit 1 chemistry, right? As a ligand exchange, carbon monoxide is a much stronger ligand with hemoglobin, right? So looking at stuff like that, it prevents effective oxygen transport through the body. It can cause headaches, nausea, dizziness at high levels, and loss of consciousness of or death, right? So at high levels, loss of consciousness or death can be a symptom, right? Sulfur dioxides now, these come from burning, right, fossil fuels. So the environmental impact now, we have the creation of atmospheric sulfurous and sulfuric acid contributing to acid rain. So we have sulfurous acid, which would be H2SO3, and sulfuric acid, which is H2SO4. Acid rain damages vegetation, aquatic life, soil quality, and infrastructure. And we know that we have health risks, right? So it causes respiratory issues, eye and throat irritation, etc. Right? So we have that for sulfur dioxide or sulfur oxides generally, because sulfur dioxide create the sulfurous acid and sulfur trioxide create sulfuric acid. Right? We also have nitrogen oxides, mainly nitrogen monoxide and nitrogen dioxide. They're primarily coming from engines. So when you see the truck on the road and the car on the road and the buses on the road and they're just going down the road and you see that brown photochemical smog just coming out, the exhaust fumes coming from it, a high percentage of it is actually sulfur oxides and nitrogen oxides, right? So they are primary pollutant emitted directly from engines, while sulfur dioxide is a secondary pollutant formed from the atmospheric oxidation of the monoxide, right? So we have respiratory issues stemming from that, and it's also used as catalytic converters, right? We can use catalytic converters in the vehicles to actually reduce that, right? So we can look at the fact that it contributes to acid rain and photochemical smog, right? But we can control them by having catalytic converters in vehicles. So in some vehicles, they would have catalytic converters which will now change that monoxide into nitrogen and oxygen, right? So that exists where we can do that, all right? Lead as well. So formerly added to petrol as tetraethyl lead to prevent engine knocking. Now largely phased out. Right, lead can actually be found in some of these things. Right, lead acts as a neurotoxin that affects brain development, especially in children. And it can cause gastroenteritis or just gastrointestinal, renal, and reproductive issues. All right. We also have volatile organic compounds (VOCs), incomplete combustion, evaporation of fuel solvents in industrial emissions. These different things are the sources, right? So general combustion, use of fuels, solvent and industrial emissions, right? That's where we can get them from. Many VOCs are carcinogenic, for example, benzene, right? Others disrupt hormonal and developmental processes. So we have that now. So for the environmental effects, it will react with the nitrogen oxide in sunlight to form photochemical smog, which is ozone and PANs mixed together. All right, we have that there. So nitrogen and its oxides now, looking at the nitrogen cycle. So looking specifically at nitrogen and its oxides, we must remember how the nitrogen cycle works. We must remember the presence of nitrates, nitrites, ammonium, and these different things, right? So through the nitrogen cycle, right, we'll have the recycling of nitrogen oxides within the atmosphere. And this is taking it completely from a chemical point of view, right? So it can be a lot. That's why I put it in a tabular format and I have this diagram over here. Just in case people see the amount of reactions and then start to like tweak, right? So let's just have a look at this, right? So we have the context, the reaction, and the description, right? So how we have the oxides being produced. hmm So we just have how the oxides are produced in different environments, right? So thunderstorms and engines can produce nitrogen monoxide, right? Or nitrogen dioxide. Denitrification allows the rise of dinitrogen monoxide and nitrogen gas in the atmosphere. In the stratosphere through UV exposure, we can have the prevalence of nitrogen monoxide and nitrogen radicals, right? We can also have the creation of nitrogen gas and oxygen radicals, and we can also have the creation of oxygen radical and two modes of nitrogen monoxide, right? We can also have the creation of nitrogen dioxide and oxygen gas, right? So there are different ways we can have nitrogen oxides appearing, right, and recycling within the atmosphere, all right? And we have the descriptions there as well. So a general acid rain cycle here that we can look at, all right? General pollutant cycle. It's really and truly a pollutant cycle before acid rain, really and truly. So the sulfur oxides and the nitrogen oxides are the movement of the pollutants throughout the atmosphere. right? Or through natural sources as well, we can get the nitrogen oxide. Natural sources that would be through denitrification using nitrosomonas and other bacteria, or we can get nitrogen oxides through volcanic eruptions, etc. Right? So we have man-made and natural sources of the oxides, right? We have gaseous pollutants in the atmosphere, right? They can actually just drop or fall to the ground in dry deposition, right? Or the particulates pollutants in the atmosphere now mixed with the gaseous pollutants now will mix with cloud water and precipitate as acid rain, right, and other forms of deadly chemicals, right? So we're just looking at the process by which these oxides enter our atmosphere and are deposited onto the land, all right? So for acid rain now, we can see this. So formation of acid rain, we have over on this side the tabular, and we have the diagrammatic format. All right. So from homes, from vehicles or different industries, we have the production of the nitrogen oxide and the sulfur oxides, right? We're gonna have what we call photooxidation, right? So the photooxidation really leads to the production of the dioxides, right? So the photooxidation will allow a monoxide to turn into a dioxide, a nitrogen monoxide will turn into a nitrogen dioxide, a sulfur monoxide will turn into a sulfur dioxide, a sulfur dioxide will turn into a sulfur trioxide, right? Hopefully you get what I'm saying. Just photooxidation there, right? Pollutants will mix with water and other chemicals, and then we have wet deposition as acid rain, right? Or it can come down as snow, then melts into rivers and surface runoff. Or we can just have the dry dust particles landing on the soil, right, which are in the water that will increase or, well, it will decrease the pH, leading to more acidic water and bodies or acidic soil pHs, right? So you have things like this. So we just need to have a general understanding of what is happening here. Mhm. So the acid formation here, this is another depiction of acid formation. Notice I have two depictions of acid formation, right? This is another one. We know we're talking about our nitrogen dioxide, our sulfur dioxide, and nitrogen oxides, right? We have oxidation here, so you can see the actual chemical symbols, right? So I have that there. We have dry deposition onto the ground. The particles just land onto the ground. That is possible, right? Or right, we have oxidation, and then they are dissolved into water, atmospheric water vapor, right? Then precipitation occurs where we have acid rain, right? So we have things like general acid, hydronium ions being deposited onto the ground, or of ammonium or nitrates and sulfates in the presence of nitric acid and sulfuric acid, right? So we have these things being deposited onto the ground. All right, and we must know the adverse effects of nitrate of acid rain. All right, speak about soil and water pH. Think about the detriment to roads and infrastructure and buildings as acids tend to break them down. Right, think about the health risks, right, of human exposure to acid rain. All right, thinking about all those things. And we have methods of control and prevention of atmospheric pollution, right? So that is it, right? So the prevention, so the alternative fuels, we can use biofuels or fuel cells or hydrogen production via steam formation or electrolysis to produce alternative fuel mechanisms, right? We can use catalytic converters, which uses platinum rhodium catalyst to convert carbon monoxide, nitrogen oxides, and carbon dioxide to nitrogen in vehicle exhausts. We can use mass transit. So instead of everybody using their cars and driving their cars and such like that around the place, we can prefer mass transit or public transport, which will reduce the level of vehicle emissions or the amount of individual cars on the road. Right? Those are the preventative techniques. We also have controlling, so sequestering. So carbon dioxide is chemically bound to form stable carbonates. So we can do that. Right? Filters. We can use filters such as scrubs, stuff like that, right? So particulates are moved from exhaust using air filters and or electrostatic precipitators, right? So in factories, when they're releasing all of these different oxides into the atmosphere, we could actually funnel or filter out the particles of the oxides, right, and use them for other processes. Washers dissolve gaseous pollutants in liquids to remove them from emissions, right? So we could spray water, right, to dissolve these particles in solutions, right, to actually produce sulfuric acid and those type of things, rather than allowing it to enter the atmosphere. We also have scrubbers, which are neutralize acidic gases, right? So, well, they neutralize rather acidic gases using alkali, which we call flue gas. We have desulfurization using lime or limestone. And we spoke about desulfurization specifically in the sulfuric acid industry. All right. But that brings us to the end of looking at atmospheric chemistry as it relates to module 3. All right. That brings us to the very end. So remember, it's really and truly